Hello again. This is Ryan, and I'm here to begin section 4.5, which covers the method of substitution in integration. Given that this is the first video that I will make involving integration, and that most of us have come off a long summer, and before that, the complete change in the way that classes were run due to the coronavirus crisis, I thought I'd begin with some review ideas that we need in order to proceed in this chapter. And then once we have those down, we'll move on with the substitution method itself. So here's a quick review of the idea of integration. So what you should have had in your previous classes is the idea that integration is the opposite process to differentiation. So it's an inverse process. But when you learned integration the first time, you learned it from two different perspectives. And the big insight of Leibniz and Newton was to put those two perspectives together. So what you should have learned was that on the one hand, when we talk about integration, what we mean is anti-differentiation. On the other hand, by integration, we mean the area under a curve. And really, when I say area under a curve, I mean signed area under a curve. So these two problems, when you saw them in your introduction to integration, would have looked on the one hand like the integral of e to the x dx is equal to e to the x plus c. This is a type of integration called indefinite. On the other hand, problems like area under a curve, you did that with approximation theory typically when you see it for the first time. That looks something like the integral from 0 to 1 of e to the x dx. When you make that assertion, when you write that statement down, what you mean is the area underneath the curve e to the x between 0 and 1. So you're looking at this area in here. And the fundamental theorem of calculus was the tool that you use to move back and forth between these two ideas. Or you can calculate an area under a curve using anti-differentiation. So the tool that you use to get back and forth is called the fundamental theorem of calculus. And so I want to remind you what that looks like. Okay, so let's recall what the fundamental theorem part 2 actually says. And that part 2 is the connection between antiderivatives and areas underneath curves. So the fundamental theorem of calculus. And this is part 2. So here's the pieces that we need. We're defined on some interval a to b. So this is an interval. And we have a function f that is continuous on ab. And that continuity condition is very important, as we'll see further on in the class. And let's say that capital F is an antiderivative of lowercase f. And so when I say that a function is an antiderivative, what I mean is that is f prime is equal to f. Or if you like Leibniz notation, d by dx of capital F is equal to little f. So f is an antiderivative if its derivative is little f. Then the definite integral from a to b of f of x dx is equal to the antiderivative evaluated at b minus the antiderivative evaluated at a. Okay, so one of the things about integration that makes it so useful is that it's what's called a linear operation. So integration is linear. What that means is that it plays nice with sums and scalar products. So I'll put that in parentheses here. Plays nice with sums and scalar products. So what I mean by that is if you take a function and multiply it by a number, the integral doesn't change. A fancy way of saying plays nice with sums and linear products is that it plays nice with what are called linear combinations. So what I mean by that is the integral of AF plus BG dx is equal to A integral of f dx plus B integral of g dx. So I can take an integral and I can split it up over sums, and if I have scalars inside, I can pop them outside of the integral. This is how you learn to do, for example, the integrals of polynomials. So as an example here, when you do an integral of something like x squared plus x plus 3 dx, what you're really doing when you calculate this is you're actually breaking this into the integral of x squared dx plus the integral of x dx plus 3 times the integral of 1 dx. So you've actually taken the integral and you've applied it to each individual piece of the polynomial. And as long as we have scalar products and sums, this is a very nice way to compute integrals. So the issue happens when we have to deal with products. So what about products of functions? So as an example, consider the integral of secant x tangent x dx. This is a product of functions on the inside because it's a secant times a tangent. Now, if I recognize a product of functions as a derivative, this is very easy. I know that the antiderivative of secant x tangent x is secant x. Because the derivative of secant x is equal to secant x tangent x. So if I identify a derivative, I can always undo it into its antiderivative, which is what the integral is asking me to do. The problem is, some functions are not obviously derivatives. It's a problem. Some functions aren't obviously derivatives. So let's look at something more complicated. What about this? So what about the integral of 2x e to the x squared dx? Now you may recognize that as a derivative of another function very quickly, or you may not. It's much harder to pick this out of products than it is out of sums. Unlike with a sum, I can't take the integral and just apply it to all the pieces in the inside because this is a product of functions. So the question is, how do we proceed? Most of the functions that show up in real life are products. They show up in modeling, they show up in engineering problems, they show up in physics. Most functions that we deal with have to involve products. So there's not going to be any way around trying to compute derivatives or antiderivatives of these functions that involve products. So we need some sort of strategy for how it is that we're going to be able to find an antiderivative of a function that is a product. So a question that we might have is, or maybe an observation, is an answer to the question, when do products show up when we take derivatives? So one answer is, so the question is, when do products show up? When taking a derivative. So one answer is when we use the chain rule. okay? So remember that if you ever have a derivative of a function that's a composition of functions, so remember that the chain rule says that if you have a derivative applied to a function with another function inside of it, so that is f composed with g, then the way you compute that is you take the derivative of the outside function and then you multiply by the derivative of the inside function. So this is a very easy way that products show up in derivatives. So when you're looking at an integral and there's a product on the inside, one thing you might hope is that that product really was secretly a chain rule from a function, or it was the result of applying the chain rule to a function that was a composition. So the topic of today's lesson is substitution. So substitution is a strategy for undoing the chain rule. It's a way of reversing the chain rule, recognizing when I'm looking at a function that is the derivative of a composition. Recognizing when we are looking at the derivative of a composition. Okay, so let's be a little bit more formal about what we mean by the chain rule. And then we can try to use that to uncover a substitution rule that we can use on integrals to undo it. So the chain rule says formally that d by dx of f of g of x is equal to f prime of g of x times g prime of x. And what that means is, because remember that an integration means anti-differentiation, that if I saw the integral of f prime of g of x times g prime of x dx, if I could recognize this thing as the result of a chain rule, I could write down that this was equal to f of g of x plus c. So the game is going to be, how do we recognize that? So one approach to this is, when we're looking at an integral, and it might possibly be of the form f prime of g of x times g prime of x dx, one thing that I could do here, so on the one hand, I already know that this is equal to f of g of x plus c. If I see that integral, I could write down f of g of x plus c. So what I'm going to do is a strategy called change of variables. Change of variables. So I'm going to introduce a new variable. And that new variable is going to be u. So let's just let u be equal to g of x. And we'll see what the computation looks like, or the equation above looks like, when we've done u is equal to g of x. So if u is equal to g of x, it's also going to be convenient for us to call f prime equal to little f. So when we're up here, and we're looking at f prime right here, this is really little f of g of x, okay? And so capital F is the antiderivative, and f prime is supposed to be little f, okay? This is where the substitution happens. The substitution that we're going to do is, we're going to take g of x, and we're going to substitute a new variable u into its place. So I'm going to start working with the equation that I've already got here. The integral of f of g of x g prime of x. So what I've done here is I've replaced f prime with little f. All I did was change the name. It's the same function. Okay. That is equal to capital F of g of x plus c, because that's all an antiderivative does. This undoes the chain rule. But I could replace g with u. And furthermore, I know that capital F is equal to the integral of little f. Now you might wonder where the plus c is gone. That just got absorbed into the integral. So when I'm looking at an expression like this, f of u plus c, if I rewrite that as an indefinite integral, I know that when I do this step, I'm going to have to do a plus c anyway, so it's okay to take the plus c from this line and to think of it as being contained inside this antiderivative expression right here. So where did the substitution happen? So right here in this expression, all I've done is I've taken the capital F prime that was right here, and I've replaced it with little f. So that's just a name change. I haven't done any math there. Then everywhere that I saw a g of x, right? So here is a g of x, here's a g of x. I can take that g of x and I can replace it with a u. So that is the substitution step right there. And what that gives me is another way of identifying when I'm looking at a function that is the result of a chain rule. So if I can make this substitution, then that lets me undo the chain rule in a way where I can just calculate the antiderivative of little f. First, we should formally state what the substitution rule actually says. So the substitution rule says that if u is equal to g of x is a differentiable function, and we know that it has to be differentiable because there's going to be a g prime of x running around in the formula like we had before, and the range of u is an interval I, and f is continuous on that same interval, then the integral of f of g of x, g prime of x dx is equal to the integral of f of u du. Now you might wonder about all these technical conditions. So you need to have the differentiability here because you can see that g is going to have a derivative taken here. The other two conditions are just making sure that because we're working with compositions, that whatever comes out of g feeds correctly into the domain of f. So this isn't going to be much of a big deal when you're doing your homework exercises that are related to practicing how to use the substitution rule. But when you're actually working these things in practice, or when you're in upper division mathematics or engineering classes, checking to make sure that functions feed into each other correctly is actually a very important part of using any sort of technique from calculus. So the key ideas here are as follows. We are undoing the chain rule. Which is really what we mean by undoing the chain rule, if you want to be more technical, is that we are finding antiderivatives that are compositions. So u is equal to g of x. And typically when we're finding a u to guess in an integral, what we do is we guess the most complicated expression inside another function. So I'll highlight that when we start computing examples and show you what your guessing strategy should be. But because, remember, we're working with compositions and trying to undo them, typically what's going to happen is the most complicated expression that you see in an integral is going to be the piece that was composed in the original function that was taken the derivative of. 2. du is equal to g prime of x dx. Now, that's a differential expression, but the idea here is that when you're using the substitution method, you don't just have to replace the expression that you found as your u, but you also have to make sure that the derivative of that expression appears somewhere in the integral as well. And this is typically where the computation happens or anything complicated. The third piece is, hopefully after you've done that, the result is a table integral. If you do a substitution and you end up with an integral that you still can't integrate, either you've done an incorrect substitution, or it could be a more complicated problem where there's more than one step involved. And we'll see more of those as we get some more integration techniques later in the course. The next video will cover the technique of substitution as applied to examples.